All right. Hi, guys. Thank you guys so much for coming to the final advanced track workshop. And today it's just going to be us wrapping everything up and just going over the guided project that we kind of like started last week. And as always, you can fill out the feedback form. You can also get access to the slides there. We always appreciate any feedback you guys give us. All right, perfect. And here's a little plugin from our projects team with Advit, who's going to tell you guys a little bit more about some like next steps you guys can take after advanced track.
Hey everyone, I'm Advit, not Frank, it's a long story, and I'm here to talk about projects. So as part of ACM AI's projects track, you'll get to implement what you've learned in advanced track to create deep learning models to solve important challenges. For example, some teams this quarter are working on detecting diseases by looking at the leaves of cassava plants, which are an essential ingredient for both food and medicine. And other teams are working on not only detecting, but identifying distinct humpback whales by looking at specific markings, outlines, and other features of their tails. So it's pretty cool stuff. And projects takes place over the span of a quarter, in which you'll be working as part of a team to develop models such as these. I definitely recommend checking it out. It's a lot of fun and a great opportunity to continue both growing and applying your skills. And the only prereq to join is having gone through advanced track. So I think everyone in the Zoom call is good to apply. And I'll drop the interest form in chat for spring quarter, and we'll send out applications to people who filled that interest form out. And additionally, if you have any questions, feel free to check out the FAQ link on the slide or send me a message through Zoom. I'll be here for a few more minutes to answer any questions as need be. And thanks for hearing me out, and I'll pass it back now.
Right. Yeah, thank you, Advit. And yeah, you guys should definitely check out AI projects. It's honestly a really great place for you guys to just gain more experience and further explore these topics that we cover in advanced track. All right, so today's content, it's going to be a little bit more on, I guess, like the lighter side. We're just going to kind of like outline and go through the project. There's going to be a lot of content that we use from the PyTorch workshop. And we're just going to hopefully finish up the project and answer any questions that you guys may have. All right, perfect. So the project, just like a quick recap. So essentially your task is just to create and train a CNN as a classifier for the CFAR 10 dataset. And so you can do this by creating a Jupyter notebook and running it on the Conda environment that you have set up earlier. And a lot of the code that you will be writing will be very similar to the code that you guys have seen during the PyTorch workshop. And yeah, so essentially you are just going to be able to take what you've kind of like seen and have been exposed to and just kind of like adapted to work with this data set instead. All right, and another really useful thing that we have available is the documentation. So PyTorch documentation is going to be extremely helpful in this project because it's really great since it outlines essentially a lot of like the functions that you might use and like explains how do you determine like which parameters you should pass in. And whenever you guys like have any questions, you guys can always ask us, but you guys can also always consult the PyTorch documentation. It's extremely detailed and thorough, and either way, you'll be able to find like whatever information you might need. And then just for, I guess, like more specific parts of the PyTorch documentation, we have decided to give you guys access just to a couple of like links within the documentation that we think would be especially helpful for this project, such as like the convolutional layers, the max pooling layers, linear layers, as well as other things that could be very useful when you're building this model. All right, and then just to give like a quick overview of the CFAR 10 dataset, this dataset contains about 60,000 colored images, and your job essentially is to create a model that is able to classify all of these images into its 10 appropriate classes. And you guys are able to download the dataset using a library built in with PyTorch. All right, perfect. And before we go into like just like the guided projects like skeleton code and like go over like the code itself, just any like quick questions about like anything? Okay, cool. So I guess we can, oh, let me see. Oh yeah, so I think Jeffrey is asking a question about projects. So Advait, if you want to take that.
Yeah, of course. So projects is 2 meetings per week. It's from 6 to 8, at least that's how it is this quarter, on Mondays and Thursdays. So for example, I'm in a projects meeting right now, but that is subject to change, but that's kind of around what we're looking for. But of course, you can work with your team to figure out a time that works best for everyone. And teams are around 4 people, and you can also choose or request who would like to be in your team. So it's pretty flexible in terms of the time commitment, as long as everyone on your team's on board.
All right, perfect. Yeah. So, are there any other questions about like projects or like anything about like the guided project? Feel free to like put it in the chat and we'll try to get back to you guys. Okay, cool. Yeah. So, if you guys have any further questions, you guys can just like put it in the chat and then we'll answer it from there. And then I guess now we can probably just move on to like the guided projects like skeleton code. Yeah. So, if you guys don't have access to the slides, it should be in the feedback form that we sent in the chat earlier. And here you'll find a link to the guided project skeleton code. And all we just ask is that you guys download the following notebook and you guys can open it in your Jupyter lab, or you can just like type it in your like Google Colab. And this is what you guys are going to be using to just follow along with the project. Okay, perfect. So I guess like before we go into the details of like the guided project, we just wanted to do like a quick like wrap up just to kind of go over like all of the concepts that we've learned. Yeah, okay. So yeah, like we said before, this is the last meeting of advanced track, and we have essentially covered like feed forward for neural networks, the theories, as well as like the implementation. We've covered backpropagation, CNNs, RNNs, and LSTMs, as well as like how to use like Anaconda and PyTorch. And so you guys, congratulations on like making it to the end. We're very proud of you guys, and thank you so much for like sticking it through. Yeah, and then a lot of you guys might be wondering like what might be next after advanced track. Well, so on the next slide, we actually have a list of other topics that if you guys are curious, you guys can totally explore on your own. And in the future, when we have like other available tracks, we might cover these in more detail. But if you guys can't wait, you guys can always look into these topics on your own. And yeah, so besides like further exploration on your own time, there are also going to be like the projects team that we have where you guys can definitely get a lot more hands-on experience with these projects. All right, so now that we've kind of like wrapped everything up and like gone through everything, I'm going to hand it over to Nikhil to go over the skeleton code.
Awesome. Thanks, Angeline. All right, just notice in advance, everyone, if you hear any background noise, sorry about that. Got roommates, so it happens, I guess. But yeah. Anyways, hopefully you all have like this screen open. So, okay, it should be called Skeleton Guided Project. And it should have this first section here. Can everyone give me a thumbs up when they had this code open? Is that everyone? I think that's everyone. Oh yeah, for y'all do half of it last week. Well, hats off. Yeah, I mean, that's pretty impressive. You did it all on your own, so great job. Hopefully, oh yeah, we did talk about this on Discord, yeah. Hopefully this just serves as like a bit of review. And also when we ask for like participation, you can like swoop in and help out when people and whenever needed, because there's a lot, as you know, there's a good amount of to-do sections that we all have to do together, and you can probably help out for those sections. That's okay, we'll work through it together nonetheless. So yeah, don't worry about it. All right, so first thing is that, okay, we're making a CNN, as Angeline said, to classify a data set called CFAR 10. And so a good amount of this is like from a tutorial from PyTorch. So if you want to check that out, go ahead on your own. But we'll be going through it as well right here. So the first step is I recommend, if you want to make your own changes, to save a copy in your drive. So click that button. I'll just make the changes here because I can edit this stuff, but I'd recommend if you want to have your own copy for future usage to make a copy. So cool. Not everyone has a copy. Let's go over the first step, which is libraries. So, okay, in theory, we could do this all on our own, but like it's not practical, right? We don't want to be implementing every single machine learning thing ever. So we have some libraries. So first off is PyTorch, and so we talked about PyTorch a bit in the past, but this is basically our core machine learning library. So everything with neural network layers or neural network architectures, PyTorch is going to have it. Next is NumPy. NumPy is called NP for our implementations. This is everything with arrays is going to be with NumPy. Next, Matplotlib. This is our plotting library. Torch Vision is going to be a library we're going to use for our data set. And then again, we have torch.nn and torch.functional, which are subparts of the Torch library, which are for neural networks and for functions, respectively. I'm going to run that, but any questions on those libraries?
Do you need to import those libraries separately, even after you have imported Torch already?
Technically you don't. So yeah, great point. So technically, like these 2 points, like so torch.nn as nn and torch.nn.functional as f, those are already implemented when you implement Torch, yes, or import Torch. The reason why we do this is because we're going to use the neural network like the sub library, or like a subdivision of a subdivision, and the functional subdivision a lot of times. So instead of always typing out torch.nn like, for example, lit.linear, for example, or torch.nn.functional like sigmoid all the time, you can just make them called f and nn, and just use like the short forms instead. So the reason why we're doing these imports is because of for I guess convenience rather than this is like a requirement sense. Does that make sense? Like it's not required, yeah, but it's more convenience.
So is it just like kind of to help with readability, or?
Yeah, readability and laziness, I guess, is a good point. A good way of saying it. Programmers are kind of lazy, so writing torch.nn every time or torch.nn.functional is not recommended, I guess.
Okay, thank you.
Yeah, of course. Great question. Yeah. Cool. So next part is, I guess, about I guess our type of CPU or GPU, or like I guess the thing we're training on or making a model on. So a really important part of PyTorch is that it's able to like really easily put your model, like I guess like turn the code that you wrote and like run it and train it on the GPU. And so GPU, basically, we can use that to parallelize our training and as well as our testing, so that we can run stuff a lot faster. And so this code over here basically checks for the existence of a GPU, and it uses that if we can. And so you can see here, if we run this, we get like it's running on GPU and the GPU name. So hopefully, because we're all these things on the Python notebook, you should get this side of work. So it should have an available GPU. It should find the GPU and then print running and device name. If it doesn't, you can probably check these settings over here. So I think it's this. Oh, not that one. this one. And then I believe this one, connect to a custom GCE VM, should hopefully allow you to use a GPU. Oh, Jeffrey, running on Jupyter Notebook. Not the end of the world, I guess. That it is really convenient to have Jupyter Notebooks, so no worries. Hopefully the training shouldn't be too long. I don't think it should be too long because our model's not the most complex model, so it should be fine. This is just more like a quality of life thing. Like if you ever made a bigger model and you want to use like you want to use a GPU for speeding it up, you could do that. And also Pritam says like you can always like save the file and open it and go out later, so that also works as well. Either way though, it shouldn't be too big of an issue. This is more of a nice to have, not required steps. All right, cool. Any questions on this code? All right, cool. So last thing we're going to talk about before we go to our first like active coding section is the data set itself. So we're going to use a data set called CFAR10, as we talked about before, to as a base data set. So we have here that we're going to use that method, the corresponding method to load that. So it's called torch vision.datasets.cfar10. And we're going to pass in some arguments on what to do with it. If you would like more details, you can always hover over this and see. So as you can see here, we're saving the data to the directory called to our current directory and then saving it to CFAR10. And this is happening because download is equal to 2 later on. And we're calling transform, and we're gonna transform the image. So this is gonna return a bunch of images, and we're gonna turn that into tensors. So that's kind of high level, but don't worry too much about it. The main things here that we're downloading this data set, downloading it to a folder on the cloud called CFAR10. And then we're going to turn them all into tensors so we can work with them better. Cool. Any thoughts on that? And there's 2 parts, training and testing data set. So that's the only distinction. But otherwise, these are exactly the same lines. Any thoughts? What do tensors do again? Great question. So tensors are very similar, I guess, to NumPy arrays in factor like there's like bunch of numbers. But the great part about tensors is that because PyTorch, they're made in PyTorch, they can be used to like automatically track like gradients or like operations that are done on them, and we can easily perform backpropagation as well as like basically calculate gradients really easily because of the fact that like it's basically automatically calculating the gradient for us while we do operations. So like these tensors keep track of operations that are happening to them, and as a result, it's easy to figure out things that we like, figure out gradients that we need for backpropagation and things of that sort. So they're like NumPy arrays, but like have some extra functionality, and that makes them nicer for for neural network purposes. You've also got some cool functions that you can also apply to them as well, but that's the main thing, that you can easily backpropagate or differentiate them. Yeah. Cool. So now that we have that in place, let's move on to our first coding section. So we worked a bit with data loaders in the past. I believe in our last workshop for PyTorch, we talked about a class called data loader. And so we have our data set, right? We want to make it easy to work with. So we want to use torch.utils.data loader to transform this data set into an easier form for us to access. So I'll give you all like, let's say 3 to 4 minutes to think about this. Of course, it's not too much time, but just to get some thoughts done. I'd recommend going to the documentation for this site for this method if you don't remember how we used it last time. And that should help out. Or if you're lazy, like me, you can type in this, and it'll tell you what arguments are there. It's a lot of random arguments, but like the most important ones are near the top. So it'll tell you what arguments to pass in, and you can determine which ones are important. Or yeah, as Pritham says, you can like we did this like 2 weeks ago, so you can use a similar concept from what we did 2 weeks ago here. It's actually the same concept, but we'll do it again. So I'll give you all 3 or so minutes to think about this. And if you have any questions, feel free to ask as well. All right, I know I said 3 minutes, but it's 2 parts. So I'll ask real quick. Anyone have any ideas for the first part at least? Remember, it can be like anything. You don't have the full thing thought out. Ideas work too. Or questions. Oh, okay. Oh, you got both of them. All right, cool. So Jeffrey has some code for both of them, and he uses this train data set. Bat size equals 16. Shuffle equals true. And that's for the first one. And so yeah, this should work. And so remember that as Jeffrey pointed out, our first argument is the data set. So that is going to be train data set, because we're doing the train loader here. Next argument will be batch size, which we set to 16. There's no requirement for this. This is obviously a testing thing. So I think, yeah, it shouldn't really matter too much. Maybe some number changes, but yeah, it should be fine. Usually a power of 2 is a good idea, I think. And lastly, shuffle equals true is just nice to have, so that between epochs when we train, we will have a random order of samples to look at. So that should help out a lot. Okay. Any questions on this input? does this step basically split your data sets into batches? Yeah, kind of. So it's like the data loader, like as you said, is like a nice, I guess, utility class for creating batches from your data set. And then since shuffle is true, it'll switch them around whenever you like have like a new epoch basically. So yeah, it's basically a nice class for creating batches. So like it makes it easier to like create like batches in general. So yeah, you're right. And then so yeah, the same kind of concept applies to test data. We're doing the same thing, but on our testing data set. Yeah, and so that should be good. If you're confused by so there's a lot of other arguments as well that are in this function. Like look at this declaration, it's like really big, but like we don't need all those the majority of them, so like don't worry about them. Ones that we need are the first three, and you can see that most of them have either default values or optional, so we are totally fine to not ignore them for now. If you're interested in the other like I guess parameters, feel free to look at documentation for more details. They have some pretty cool stuff there, but for now we're going to be dealing with this base level stuff. So yeah, let us. Actually, I don't think I ran this because I forgot. I'll run this too. So hopefully you ran this, and I ran this earlier. It'll take a little bit of time, but hopefully not too long. And then after that, we can run this next statement. Cool. And then we can run this. Cool. And then we can run this. And then we see, so this is just some sample code that we put together to help you all like basically see what some of your data looks like. And so note that now that we have a train loader, we can like basically index into it or like get elements from it by creating an iterator on it. So if you type an iter on this thing, we create an iterator object on top of that. And so what that means is that we can use the next command to get individual like data objects from that train loader. So if you think of it as like a list, and then whenever we call next, we're going to go to the next element in that list. And so in this case, we're going to have a collection of batches of images, and then calling next will go to the next batch. So as you see here, we call next and we get the next batch of images and labels. So the features are the images, and the labels are like the labels we're trying to make our model learn. And then so this is going to be a batch. So a batch is going to be 16 images, image label pairs. So we're going to take the first one and just look at that one. And so we are going to use some matplotlib functions to plot that picture, as you can see here. Also going to modify the image as well. But yeah, the main things here are that we're going to be taking part of our batch, one of our batches, one of the images from that batch, and then showing it on the screen. So yeah, here I got a horse. It's probably different for you because of the fact that we have shuffle as true. So it will be the same likely, but yeah. Any questions on this code? We're not going into too much detail about like plotting stuff, but it's cool to look into in your own time if you ever want to look into it. Cool. Now we can move on to the big chunk of it. This might take a bit of time, but now we're at the stage where we can start looking into like how we want to implement a model. And so we're going to be implementing our own version of a CNN based on what we talked about in our slides a couple of weeks ago about the our structure of a CNN. It's like a pretty common structure for like a not too deep CNN, so we're gonna stick with that. We've already written like a bit of code for you all, like the base class declaration as well as the two main functions we're gonna need. And so we're gonna let you all take a bite at this challenge. If you all need some help, remember, let me see. We have dots here, but remember that the structure of a CNN is with a convolutional layer into a max pooling, and then we had another convolutional layer on top of that, and then we had a flattening layer, or like we flattened that all afterwards, and then we stuck them through a linear layer at the end. And so I recommend using that structure. And it's probably a lot of stuff, so I'll give you a few hints. So we will want to be declaring some layer, like in the initialize, we want to declare some layers here. So for example, we want to say like conv1 equals, and then remember that we have the NN class for a lot of our stuff. And so there are, oh, too deep, things for NN dot, yeah. So a lot of stuff here. Conv2D is interesting. NN dot linear is interesting. I think there's also a flatten method as well. So look into these methods. I recommend starting with those. But use initialize to declare layers, and then use forward. Let's start with initialize first. So let's declare all of our layers first. So I'll give you all like 5 or let's say 3 minutes to start on it. We'll all come back together, and then I'll give you more time if needed to think about it more. So yeah, I'll give you all 3 minutes or so to think about how you would implement these or like declare these layers here. If you have any questions, of course, feel free to ask because this is a lot. But it's also like this is like the main chunk of stuff that we're doing right here. All right, cool. Any ideas on anyone's part? I know it's a lot, but let's start with ideas first. All right, Jeffrey has an idea. All right, architecture from last week's video. All right, let's break that down then. We can break that down. So, all right, so like I said, the way we're gonna do this, that I'll make a comment on this right here for that. But like maybe we're gonna do this that we're gonna have a convolutional layer into max pooling, into another convolutional, into a bunch of linear layers, right? And so there's a bit of a middle step here, or flattening, but it's not a huge step, so we're gonna avoid that. But let us start with the other layers first. So convolutionals, max poolings, and linear layers. So the way we're gonna do that is that we're gonna use nm.convolutional2D to use convolutional neural networks. So we can type in nm.convolutional2D, and it'll give us the arguments that we need to pass in, or it'll tell us, it basically give us some documentation for this. So just it looks pretty daunting, but also a lot of terms that we've seen before, right? So number of input channels, number of output channels, kernel size, and stride size, as well as padding. So does everyone remember what kernel size, stride, and padding are? Actually, can someone tell me what one of those terms is, at least in chat? Yeah, so kernel is how big your filter is, exactly. And so remember from like a couple weeks ago when you talked about CNNs, that the kernel, yeah, the slides are there for you. But the as Jeffrey said, the kernel is basically like the filter that we're going to use, or the size of the filter that we're going to use to look at nearby pixels or data in a sense. And Perry adds in that padding is when you increase the dimension by adding zeros around the edges to capture boundary info. Yeah, and so sometimes, like for example, we might have like a weird stride length plus kernel size combo. So we have to add padding. But other times you just want to add padding just to add some extra space to the edges. So padding is really important. And Jeffrey says, don't know why this is, but like I mentioned, padding is equal to kernel size minus 1 over 2. Let me think about that. I might have covered that. Kernel size minus 1 over 2. My guess to be why that would be the convention is because of the fact that in case your kernel like moves out of the frame, you don't need to have like the kernel cover like the entirety of the next frame, but like actually, why did it be not minus 1? Okay, but I would expect that this kind of convention would be used in the case where like your kernel plus drive combination leaves itself so that, or like ends up in the case such that you get to the edge of the image basically, but you don't have enough like rows of data in the corner. And so in that case, you wouldn't have like kernel size. So kernel size is always odd, and padding should always be even. Yes, kernel size is always odd. Padding size is always even. Yeah, I believe that's also true. I'm not sure exactly why minus 1 over 2 is the way to do it, but I have to think more about that. But yeah, that is right. That usually, I mean, kernel size is like always odd. and then padding is usually even. Yeah. So yes. But all right. Great job on that review, everyone. Glad y'all remember your convolutional terms. We are going to declare some inputs and outputs for this. So we need to pass in input channels, output channels, kernel size. We're gonna stick with the default slide of 1 and padding. So remember that all of these things like kernel size, glide size, and padding size are all up to us that are like hyperparameters. So we get to choose these. And so you can play around with them if you want. They will change the dimensions of your output, so keep that in mind. But let's go with this. So given our data set, like data set's features, we're gonna have 3 layers of, I guess, input channels, or 3 input channels. And let's say for our sense, we're gonna make it into 6 output channels. Of course, these numbers are like not like, there's no like rhyme or reason to like the output number. But we just chose this just for testing purposes. So we'll stick with that. Kernel size is gonna be 5, and padding is gonna be 2. Following that thing that Jeffrey said about -1/2. Let's stick with that. Kernel sizes of 5 and 3 are really common, so keep that in mind. But yeah, this is going to be our first convolutional layer. It was taking in 3 sets of 3 input channels from our data loader, and then it'll be turning that into 6 output channels through convolutions. And we'll be having a 5x5 kernel or 5x5 filter with a padding of 2 at the end. Any questions on this declaration right here? You originally chose 256, but then the sample said 6. Yeah, I mean, there is like no super big rhyme or reason for the output number. When you have 256 though, you're gonna add a lot of weights and stuff. That is like one thing. So when like you jump from like 3 to 256, you're gonna have like a lot of like I guess like or not weights, but you can make your vector a lot bigger at once. Which is totally, I guess you could do that. I think for us for now, I think we stuck with keeping like the linear layers at the end, the fully connected layers at the end. Do with all the big vectors because they're usually faster. But I think on 256 you could try that out and see how it goes. So yeah. All right, let's move on to the next layer of pool. Any ideas on what we should do here? So again, we have a method called maxPool2D we're going to use. And we need to pass in a kernel size. And we're not gonna worry, and a slide, I guess. So yeah. And the rest of them we're not gonna really worry about. So yeah. All right, I guess these values are kind of a little bit arbitrary. We're going to go with 2 by 2. We talked a bit about, I think we talked about a 2 by 2 in our workshop about CNNs before. But remember that max pooling basically takes like a I guess like a map, and then condenses it down based on which like the maximum value in a certain region. So with this, we're going to have squares of size 4, and we're going to slide over 2 every time. So we're going to have no overlap in our max pooling list, but of course. So yeah. All right. So our second convolution is going to take this in and then deal with it. So remember, our plan is to do a first convolutional layer, then do pooling. Now we're to our second convolutional layer. And so now it's a bit more tricky on figuring out the number the input size, but remember our, I guess like, actually no, not, but okay. Starting from scratch, we're gonna make another convolutional layer. And so we're gonna have our 6 outputs come into 6 inputs. And then I guess arbitrarily again, these are obviously all hyperparameters. You can play around with these to see the best impacts. We're gonna have 16 output channels. And then just to spice things up, we're gonna have a different kernel size and different padding. Remember that kernel size is always odd, and then padding is always correlated with that. But we're gonna stick with these values for now. Again, remember that us having a smaller kernel will result in like less weights as well, so that helps out. So that's good. All right, cool. So now that we have that, we're gonna create our flattening layer. So we're just gonna have a layer called nn.flatten. Do you guys think we need any arguments here or no? There's technically R2, but do we need to care about these? Do you guys think? Nah. Yeah, I agree. We don't need to care about these. It's like, maybe probably not intuitive to think though. But the flatten layer on default basically takes your complicated vector and turns it into one dimension. And if you play with these input features, it will change the way like your output ends up looking. So from that, and so it'll modify like which dimensions it'll actually end up using for the flattened array. So we want to use all of it, so we're gonna stick with what we have. Yeah, cool. So now that we have that, we're gonna move on to, so we have convolution 1, max pooling, we have convolution 2, we have flatten. Now we can move on to the linear layers. So let's start with the first one. So we're gonna divide the linear layers processes into 3 separate linear layers. And so you might wonder, like, why not go from like this output directly to like the outputs that we need for like a final prediction? The reason is this is because first by studies is that like having multiple linear layers at the ending is generally better for performance, but also from like a thinking perspective, just like you're gonna have more weights and more I guess like nodes in that thinking process. So like imagine, for example, if you wanted to like use a fully connected neural network in general, would you rather it be 1 layer or 3 layers? You probably say 3 layers because you just got I guess more levels of like processing and focusing on different things. So of course you could do infinite layers here too, but like that's like gets impractical. So we're gonna stick with 3. But the idea is that we're gonna create 3 linear or fully connected layers to go from this convolutionally flattened version of the convolutional output, and then we're gonna go to our final output, which is gonna be this is gonna be 1 to 10 classes. So first thing is the linear syntax. So linear is the way that you make fully connected layers in PyTorch. And so if you look at the syntax here, you'll see that it's quite simple compared to the other ones, but mostly this input features is the input or first input, and second input is output, number output features. So number of input features depends on the output of the flatten, because we're going to apply these in order, right? So might be a bit confusing at first, but from this documentation, we can actually figure out what the output will look like. So we can see here that the output is of size n, c out, h out, w out. It's all confusing, but they're all defined earlier. So let's go through those all. Oh, it disappeared. All right, we're back. So n is batch size, we have that. And then h and w, those are right? H and W correspond to sizes, I guess. And then the last one we see here, HW, I mean C. So let's go with IC. And C is the number of channels, output channels. So using the all, we can basically try to figure out what our output size is going to be. So in theory, like in practice, it's probably easier just to test it out yourself and figuring out like running the code and figuring out the size. But for now, we'll be figuring out ourselves. So the first thing, the first parameter, so you can just open this kind of annoying. Okay, finicky. Okay, so the first thing is batch size. So we know batch size. We declared it up above. We declared batch size up here to be 16, I believe. So that's the first component. The next component are C out, H out, and W out. So going back to those are basically given by like height, width, and number of channels. For now, we're gonna stick with it's given to us here. So let's go back here. And so the way it's written is 8 and 8, and we're gonna have one output channel. So it's a 1, but we're gonna ignore it for now. And then we have a batch size and an HC and H are two other like height and width parameters. And then with that, we're going to go to our output size. So this output size, again, is the thing that we get to choose. We're going to go with 256 just for our choice right now, but it's actually up to you. So feel free to play around with it if you want. Just remember this value so you can keep track of it for later layers. Next, our next layer will take that in as input, so 256. And let's say we're trying to downsize at this point, right? We're trying to go from this size to 10 outputs. So we're going to take a 128 right here. And our last one's going to go finally from 128 to 10. And so 10 is our number of classes we're trying to predict. And so we finally got there with the third layer. And so with this, we should have all of our layers for our model. And so now that we have that, we can go ahead and start trying to implement stuff. Any questions about things so far? Could you go over the part where you got the 8s from again? Yeah, sure. So, okay, those. So actually, let me open the PyTorch documentation. PyTorch. Wait, testing. Hello. Let me open the PyTorch documentation real quick, and we can go over that because that's kind of finicky. Let's go over to PyTorch.nn. How much on 2D? Testing. So testing. It applies. So the input is going to be a size N, CN, H, and W. And the output is going to be a size N, C out, H out, W out. And so we can see that N is batch size, which is we said was 16. C is number of output channels, which is going to be 1. And we're going to have W out and H out. And so W out and H out aren't necessarily, I guess, they actually aren't the same as like the input features. So you can see it like over here, this is not 8 by 8, right? It's like something else, 32 by 32. Remember that in these situations, it's fine. Let me just go over this first, but then yeah, think about that. So, okay, so where was I? Yeah, I was at the part with H out and W out, right? And so they're not actually going to be the same as their inputs. These are actually features, I guess, features that depend on like the convolutional output. And so let's see if they actually tell you where the calculation is done. Yeah, it's these calculations. You can probably go through it yourself and test it. Yeah, but these values are used for H out and W out, and they happen to be what we want. But for now, I will say that from like what we tested beforehand, that 8 and 8 do work. In other words, yeah, I guess so. Yeah, if you want to like try it yourself, what you can do is like, so what I was saying earlier, right? So when we actually like write the forward method and test it out, for example, right? Let's say like we didn't have our old code to lean back, or we didn't test it ourselves, but we didn't have anything to lean back on. What we could do, right, is that we can take we can run our model only as the first 4 lines, right? So we can get rid of these lines. And that could be forward, right? Oh, whoops. Why did it disconnect? But anyways, it could be the first 4 lines, right? And we could have return like the output of the flattened layer. And then we could print that size. And the size will tell us what we need to have this be. So you could DIY it. You could DIY it. So you could like test it that way. But for now, yeah, let's not worry about too much because the calculations like look quite annoying. The important part is that it's easily testable, so we could test it out and then see how it goes. But for now, let's stick with these values, go with it. But yeah, don't worry about it too much. Yeah. Cool. Cool. Any questions on the general model? All right. Forwarding should hopefully be easier. So let's go over that right now. So let us use our layers now. Oh, chat sorted. I don't want to choose chat there. Let's use these layers to create our like process for running forward propagation, or like feed forward. So given an input X, what's the first thing that we're gonna do? What are we gonna apply first to X? Remember, it's also an order. Yeah, we're gonna apply C1. So the order's already here. So hopefully that makes sense. We are gonna apply C1 to this. And remember that we also often have activation functions after layers. And so we're gonna attach this to a ReLU at the end for activation function. And so oftentimes you have activation functions after most of your good chunk of your layers, just to incorporate nonlinearity better, and also yeah, make the back propagation easier as well for derivative purposes. But we're gonna apply ReLU to the output of our convolutional first layer. All right, next step. What's the next layer? Next layer. Thoughts? All right. Thanks a lot, Terry. Yeah. Glad you're here. All right, cool. So we're gonna apply pool. Yes, I agree. All right. And then F dot ReLU of, yeah, it's probably better to do that way. Yeah. All right, so Jeffrey's got his code there. Basically, we're gonna apply them in order and apply ReLUs as accordingly. and we're going to return the output. And so this will take our input and turn it into our final desired output of size 10. So we're going to go from input size or whatever input size is. We're going to have 3 input features times a 32 by 32 image. So it's going to be a 3 by 32 by 32 image. We'll pass that in, and we'll turn that into an output prediction of size 10 at the end of it. So I'll write through it, but yeah, hopefully that makes sense. This goes here. Let's see, did we pull twice? May have forgotten a pooling layer. We may pull twice. I think it's better to pull up for convolution layers in general. I may have forgotten that in my first section. But yeah, other than that, should be good. We'll flatten. And then we're going to do the same thing with the denses. So let's copy this and make these dense 1, dense 2, and dense 3. We'll return X. Oh. So yeah, hopefully that should be our model. And then we're going to move on to testing it in general soon. I would say now that we have 2 people, I have a quick question for everyone. Would you all rather we continue going section by section now, or would you rather us just answer certain questions that you have since we're down to 2 people? As this is fine. Okay, cool. You're currently on training part. Okay, cool. We'll get there soon. We're almost there. But I think, yeah, we'll get through this part and we're almost there. So yeah, cool. So now we have that, right? Let us actually create instance of our model. So you all know classes. How would we create an instance of our model? We have our CNN class. How do we create an instance of it? Where'd my chat go? Chat disappeared. This is a quick one. How do you create a class, or how do you create an instance of a class in Python? Class, yes. Nice. Okay. So as Jeffrey put in chat, we're going to call CNN. And so that will create an instance of our CNN class. And so the way we knew that is because we called class CNN. And in the special method called initialize, we didn't pass any other parameters in here. And so we have an empty constructor here. That's the default constructor. That's the constructor we made. And so can do that. Hopefully it runs. And this line of code below puts the model, puts that set of weights and that set of weights and stuff onto the GPU or the CPU, whichever device you chose earlier. So it's all on that one device and it gets done there. All right, cool. Next part is a bit of review. So we are doing classification. So what should our loss function be? This is a bit of review to week 4 of workshops. Should we do mean squared error? Cross entropy loss. I agree. Yes. So remember that we're using cross entropy loss because mean squared error doesn't really work in this case. We talked about this earlier, but also because of the fact that cross entropy has a better loss function for classification and gradient descent. So we're going to go, or that. So yes, this is our loss function. Thankfully, PyTorch has a method right there for us to do loss cause entropy loss. And then lastly, I'll help you out with this one because optimizers we haven't covered yet, but obviously we talked about that a little bit about it, but gradient descent is like one way, or like the most, I guess like it's like the main way of doing optimization, but there's different variations on it. And so there's different ways to basically optimize stuff. And so the one that we're going to be going with is called Atom. It's like I guess like it's an algorithm. It's like a modification of stochastic gradient descent. But it's pretty cool and often used. And so as we see here, we have to pass in a couple of things to it. So the parameters are optimized, the learning rate, and other stuff that's also there. We're going to have a weight decay as well, but mostly it's most important parts are the parameters and learning rate. So we are going to get the model's parameters by calling model.parameters. And then let's see. Yes, Atom is pretty great. Learning rate is going to be, let's see, what's the learning rate going to be? Is there a default for learning rate? Let's stick with the default right there. And then we're going to go to weight decay right here. And we're going to set that to 1 e minus 3. This basically is one of the features of Atom. It's basically how much the weights or how much like scheduling, how much learning rate and stuff, some things decay over time. Me more about it there. But yeah, cool. All right, so we can run these two things and then see what they go. But yeah, hopefully this should be good. Anyone have any questions on this section? All right, cool. I'll pass it on to Pritam to talk about training and testing.
All right, so hopefully we got everything that Nikhil said. That's probably the hardest part of this, but we do want to train our model so it can learn. Without training, the model is not really that useful. So yeah, let's just go over that. Let me share my screen first before I do anything. Can you all see my screen? All right, so Daniel said, that's good. All right, so that's good news. So let's start off with what we're gonna first do before we start training. I know in the recording, they probably stressed this a lot. I know because they stressed it when I was in the workshops, but what do you do before you start training? It's pretty easy. You could put it in the chat or just voice it out loud. Okay. Make sure your model works. Yeah, I guess, but okay, so let's say you know it works. What do we do before we start training? Any ideas? Okay. All right, we just do model.train. So just do that. So that's like the first thing we do before we start training. So we make sure that we prepare it to train by calling model.train. So what do we do after this? We know that we want a batch size and we want to go through the training data. So Any ideas on what we do? You don't have to like give me like code or anything, but just like a high level overview would be great. Yeah, so as Nikhil said, model.train puts the model in training mode, or it just kind of prepares it for training. Yeah. All right, so I guess I'll just go over it then. I guess we could like move this line. So what we want to do is we want to go over each instance in our training data. So we could do for I and batch and enumerate train loader. So what this is doing is, oh, all right. Sorry, I didn't run this yet. Okay, so what this is trying to do is we're trying to go over all the training instances of the data. So you could, this is each index, and this would be like the batch in the training data. So we're trying to go over each of our batches in each epoch. So I guess, yeah, you parse the batches. Not necessarily. So you go over the batches, like you loop through, but not necessarily like parsing through the batches, if that makes sense. Okay, all right, so what else do we think we need to do during training? Like, what are some ideas? Like I said, it could just be high level, so. Okay, I guess, yeah, well, we could deal more with the batches, right? So we have batch inputs and batch labels. So what our batch inputs are basically our training instances without the predictions, and our batch labels would be our predictions. So let's say this is CFAR. So batch inputs could be just like a bunch of pixels, and our batch label could be whether it's like a car, a bird, or whatever you want it to be. That's in the data. So that would be our batch. So we have both the batch input and the batch label contained in our batch variable. Then we want to save all these batch inputs and our batch labels onto our device, which will then use it to train the model. So I guess it's like, it's important that you have it stored on your GPU or your CPU when you start training your model. So that's just our part for that. So batch inputs, batch labels. Oh, sorry. So batch inputs have to be saved onto your device, whichever one you're using. So I think we saw this earlier during model.toDevice. So yeah, that's what we're doing here. So device can be either your CPU or your GPU that you use to run the training on. So same thing with batch labels. So we want to save both of these. All right. And then, yeah, so once we've done that, what do we think that we're supposed to do? So this has all been just like preparing for like training and getting our data where it needs to be. So what else do you think should be implemented? You can put it in the chat, or you could just say it. You're lost. Okay, yeah, so before we do our, okay, it's the compute loss function and backprop. So there's one step before we, okay, so all of that's great, but there's like one step before we do all that. Like, how are we gonna compute our loss function without something that's missing. I mean, like, what do we need to compute our loss function? So we have our right labels, and we need something to compute our loss function. So what are we missing here? Okay, so I guess I'll just say it, but we're missing our prediction. Oh yeah, Jeffrey said it. So it's predictions. So good job on that. So we need our predictions to compute our loss function. So our predictions would be passing in the batch inputs to our model, right? So our model makes our predictions, and our input would be our instances, but not the labels, right? So not predictions. All right, so yeah, so after that, I think I'll just use your guys' answers because that's basically what we're gonna do. So we're gonna first get the loss equals the criterion. So what criterion means is we went over the cross entropy loss. That criterion could be passed in. So there are other types like yeah, so there are other types of criterion. Cross entropy loss is one of these criterion or criteria. So that's what that is. So let me put that in. So what we're doing here is essentially computing the loss with our predictions. I had this line, but IDKY, it's there. Batch inputs equals torch dot reshape batch inputs, comma 16, 32. I think that was from the, yeah, so that was from the guided, not the guided project, the MNIST classifier that we did. So you don't necessarily need that here. That's just reshaping the batch inputs to a better size for computation, I think. But I'm not super sure on that. All right, so back to where we were at. So loss equals criterion, predictions comma batch labels would just be computing our loss function based on what batch labels or what desired output we want and the predictions, like what predicted output we have, right? So after that, we can just do backprop, so loss.backward. And then after we're done with that, we can step to the next. So we can use our optimizer to implement this. So we step through the optimizer. And then, like Jeffrey said, we need to clear the zero gradient buffer prediction. So that also has to be done. Okay, so I don't know why this is over here, but yeah. So that's do, and then let's see if this runs now. Right. Yeah, so while we were waiting for this to run, what are some ideas on like what to test? Like how we would approach it? All right. Okay, so let's see. Okay, so we haven't implemented the test yet, so that's all right. Okay, yeah, so what are some ideas on testing? Model.test. Well, close enough, but not exactly. Be model.eval. That would be the first thing we do instead. So, whoops. Yeah, so we would first have to do model.eval instead of model.test. All right, Wait, what was tragic? Okay, all right. Well, I mean, it's close enough. So let's just go with that. You would expect it to be model.test because it was model.trade. So I don't blame you. Okay, so correct equals 0. Okay, so yeah, so we go through a similar approach to training our data. So, all right, how do I put it? So what was that we already had in test or train that we want in test? Let's put it that way. Labels. Okay, so we had labels in train as well, but what is a key difference that we need to do? So like we used what's the variable that like stores our test data right now? So what do we want to loop through? How about that? Okay, yeah. So that's exactly right. So let's, I guess, use a similar loop to what we did earlier. So for I, comma batch and enumerate, right? Test loader would be our thing. And then we would use similar thing that we did for training. So I'm not gonna go over that too much. Okay, so we would also have batch. Yeah, so we're gonna do the same thing. So remember how we saved the inputs to our device? So similar consumption or similar concept. So batch inputs would be saved to our device, and so would batch labels. Right. Okay. So then we're gonna do a similar thing, except here we're not really training. So this is even easier than before. So we're not training. So what would we need to do to evaluate our testing data? Compare, predict and compare. Yeah, that's exactly right. So we use our predictions. So wrong place. Okay, so predictions, right? So then we would do batch inputs. So we're feeding our testing data without our labels. So only like the pixels. So only our image data, but not our labels. Then we compare it to the labels that we have. So predictions would be, okay, so this is our prediction. And what we do here is we're going to do argmax axis equals 1. So what is that exactly doing? So we have a bunch of predictions, but we want to take the maximum argument of all our predicted probabilities, right? So we have all our classes, but we want to pick the class that has the largest probability of happening, according to our model, of course. So that's what we're trying to do here. Then once we do that, we're gonna append to our how many correct we got, right? So we want to keep track of how many correct we got. So I didn't go over why correct equals 0 was already here, but now I am. So we're going to say whenever our prediction is right. So we're just gonna like add it to it. So like predictions, whenever that's right to batch labels, right? So when our prediction matches the desired label on the data set, the testing data set, then we just add through. We add through the results we get. Then we have this end of epoch accuracy, which should evaluate what our accuracy for the testing data was. So let's just go over and run through this. Right, so okay, so yeah, that's that's gonna run. So meanwhile, if you have any questions to ask or anything that was confusing for the stuff I went over, or anything that was went over in this workshop, you could ask, I guess. Wait, is the code for the train test loop given? I don't think it is given, but I think you do have to write it. Yeah. So I guess I'll just respond. Is that what we are doing now? Oh, okay, yeah. I get what you mean. Yes, it is given. The train test loop, yeah. I thought you were referring to these loops, but no, yeah, the train test loop is given. Yes. Yeah, so if we have these two implemented like we went over, then you would already have this on your own. So let's see where we're at right now. So we're at Epoch 7. We're at Epoch 8 now. No, I didn't have it. Okay, yeah, so I don't know. It is there in the skeleton for this week. Yeah, so maybe last week's skeleton didn't have it, but not really sure. Okay. All right. So how many epochs was it? Okay, so it was only 10 epochs. Okay, so if you didn't use the skeleton, then I guess I'll just show this here. So you can take that. It was already in the skeleton, so you can just copy it over. Let me know when you're like finished. Or you could open up your skeleton. We can move on. Yeah, I think that's probably a better use of time. But it's already in the skeleton. If you look at the running the train test loop section, if you ever need it. Okay, so we got a pretty all right score. So we got 64.83% of accuracy for our end of epoch accuracy. So that might not look like it's the best, but we only did 10 epochs. So if we graph it through, you might see a lower loss over time, lower loss over time and a better accuracy over many epochs. So we can, but we don't have too much time. So we'll just leave it for you to investigate. How about that? So saving the weights. So I guess this part is not really intuitive, or we didn't really go over in the rest of the workshop series. So I'm just gonna go over this because I don't know how you would know without maybe looking at the PyTorch documentation. So we'll just go over it. So why would we want to save weights? So maybe we're running this like large model that is very complex and it has a lot of data, and we're running it on a high computational and a powerful machine. So, and maybe you don't have that much time to use that machine. After you're done running your model, you kind of have to exit, but you can save your weights. So you don't have to. You would want to save those weights because you can't do it in your local machine. So a good personal experience is with a supercomputer that I use, and I only have a allotted number of sessions that I can do. So in those situations, it would be very helpful. So you would have, yeah, so you can just copy this over. Yeah, so we use PyTorch.save, and we would use the syntax to just kind of save our model's weights. So that's a neat piece of code here. All right, and loading the weight set. All right, so maybe there's a power outage and you've lost all your weights, but you can reload the weights that we just saved. So we can save it here, right? And then we can just reload it if we saved it. So we can just make our new model. So basically what we did before, declare an instance of the CNN class, which is new model. And we just load our weights into the new model. Right, so you're probably wondering what the state dict is the same thing here. So we were having the state of the model and we just load our state back in. So then we just do torch.load and then the file that we saved it as would go here. And this should hopefully do what you want to do. Okay, so we've made it through. In this workshop, especially, we implemented a CNN from the ground up. Actually, I should probably say from the last workshop too, but we didn't really go over it. But this is not the end, or otherwise everyone would be using the same CNN model everywhere, but I don't think that's reality. So if you want to go above and beyond and just investigate CNN and computer vision with deep learning in general, you can incorporate some of these following topics. So regularization, L2 regularization, and dropout layers. So we talked about dropout layers. We also covered regularization, but dropout layers allow you to not only have fully connected layers, or you can even drop out some neurons, which make it more flexible. So that's one of the techniques you can use to amp up your CNN. And you can also check out transfer learning. So we covered this briefly, theoretically in our workshops prior to this. So you can check that out. But yeah, so I know that Jeffrey and Daniel were both consistent participants over our workshop series. So thank you so much for sticking with us till the end. Sorry for the typo, by the way, but be sure to do the anonymous feedback form. This form isn't only for this workshop, it's for the whole workshop series. So I hope you guys fill that out. But other than that, I hope that you enjoyed learning about neural networks and especially convolutional neural networks, just from theoretical standpoint and from a viewpoint of a practical implementation. And hopefully you do projects because you can use what you learned here to apply it to new and novel problems. All right, so I'd like to make a model to detect touching grass. How would I get a data set for that? Oh, okay, so what